This summary is structured around a record log I started in 1965. It is about an invention and design of a floating telescope system, which I call a Spheremount. It was conceived after experiencing the smooth motion properties of a floating crow's nest, a recreational swimming toy resting atop a pole stuck into a concrete, balanced fiberglass sphere floating in water, like an inverted pendulum. I did submit it as an invention disclosure for telescope mounting as shown here. I requested and received a release from GM to pursue the patent, which I subsequently obtained. A key point noted is that the amateur telescope maker is capable of grinding and polishing astronomical mirrors far larger than he can afford to mount. An attempt is made to identify where step increases in costs occur, as these may hint at potential cost-saving investigations. A major one appears to be when an observatory or shelter becomes required. The general motions required for tracking and support are better defined here. Tracking is identified as being quite simple if there is no need to also support the telescope. Further analysis of moving or holding alignments relative to a center of gravity begin to suggest spherical elements. Discussion continues to include the use of fluids to supply uniform support pressure over wide distributions. Here the separation gap is assessed and the potential for good damping may be possible. Most of the proceeding has been a summary intending to formalize a buoyant spherical shell concept, as the construction of a 24-inch sphere tooling has already begun. These pages will gradually transition to an as-fabricated record of that construction. Photos and records of these prototypes and tests are included in this enhanced PowerPoint record of the Spheremount invention. Incidentally, in my later professional years, I used PowerPoint as a conceptual design tool using the powerful graphics available. Covered here are alternative means of attaching to the sphere for purposes of tracking and guiding. This still remains a high-risk area, as any attachment runs the potential of becoming an angular error creating fulcrum point, as shown here. Also highlighted is the first reference to a gyro-stabilized system. The case for the gyro is that all that is needed to be done would be for the gyros to hold the sphere stationary, because for all practical purposes, the stars are fixed in space and do not move. The actual grinding of the 10-inch Cassegrainian telescope optics was begun the year prior when I still lived in Detroit. The mounting was to be of a conventional equatorial. The 10 log record pages are noted to be blank. A commercial 14-inch diameter fiberglass pressure vessel was found to be available and was purchased to serve as a proof of concept telescope housing, an older 4 1/4 inch reflector I had built years before. A fiberglass support basin was cast against it, and the two were ground against each other to make them perfectly spherical and mated to each other. With an ounce of water, the Spheremount floats free. Adding water breaks it free and it moves to a new balanced position in the lower right photograph. A log entry post of the boilerplate test is shown on the right. An excerpt of that test from my book of Firebirds and Moonmen appears on the left. Highlighted is the key element. The sphere mounting exhibits outstanding thin film damping properties, damping that matches finger tremor motions and is nearly instantaneous. A work plan is devised to turn a 24-inch diameter truncated sphere in plaster using techniques learned at Pratt Institute for Industrial Design. These photos support to show following that plan. With a sphere cast, a plan is made for layup of two fiberglass half shells, which are then assembled as one by a composite lap seam along the internal inside diameter. The tube and the basin are also shown with a few key dimensions. The plaster shells, which are cast off of the master model, will become the female tools that will make the actual fiberglass parts. Special notches right assure that the tooling will come together correctly for final assembly. This cutaway drawing identifies the interfaces and critical dimensions. The key notation here is initial flotation, and along with it, thoughts of drive systems, because of the expectations that low friction will enable very low drive forces to solve drive problems. Here are more studies to improve the clock drive and thoughts on alternative finder systems. Fabrication of the secondary holder telltales that the optics are near complete. The optics become important in finalizing the assembly. The figuring of secondaries becomes the most important and difficult of tasks. I've had to resort to star testing for a null figure to buy off the optics. And right fluid basin is refined with a 3-legged tripod. It folds into a nice package. And right, the first real wet test of the system. These are photos of the water tests. Shown here, testing of different attachments to the driven polar axis shaft, negative springs and a magnet locking to an attached metal band. Photos of the telescope in the backyard during the star testing period. Highlighted is a note that I saw and picked up a vapor trail and easily followed it up to identify it as a SR-71 traveling at a very high velocity. And here is the completed Spheremount. The belted drive attachment shown was successful, at least for visual tracking. This cutaway drawing shows the final configuration. I subsequently remounted the telescope in 1987, integrating the sphere into a forward tube assembly. Miscellaneous corrections and fixes as the telescope is nearing completion. On the left, completion and first showing of the telescope to close friends in the Santa Barbara Astronomy Club. First public showing of the telescope was at a Los Angeles Astronomy Association star party on Mount Pinos on July 8, 1967. I also participated in a grazing occultation with David Dunham and the local astronomy clubs on July 27th, and at the Stelvane Convention in Vermont on August 5th, 1967. I exhibited and entered the telescope into competition. Was awarded a first prize for mechanical ingenuity. And here are miscellaneous concept studies. Large Schiefspiegler Spheremounts. These pages represent marketing considerations based on questions and responses from the public. Wide-ranging applications for the Spheremount are considered here. And continue. August 1, 1967, a stop at the Structural Fibers facility in Ohio to show them the 14-inch diameter Spheremount that I made from one of their spheres. I left General Motors to accept an industrial design position with Sundberg Farrar as their representative at Lockheed on the L-1011. Purchase of 3 war surplus gyros from C&H Sales in Pasadena allowed me to start experimenting with gyro stabilization. On the left, the documentation of the gyro purchase, 3 of them, and a look at a longer focal length Newtonian with a truss upper tube assembly. In Los Angeles, I started a second Spheremount using the same sphere, size and tooling to make an 8-inch f7 telescope. May 5, 1968, achieved a successful suction cup attachment to the sphere to keep a star in the field of view for a period of time. Again, as demonstrated, it would not be acceptable for photographic purposes. Continuing with clock drive experiments, close but no cigar. The 8-inch f7 is now showing more detail as it nears completion. The photos on the right are of the completed telescope. The truss upper tube assembly was made from a brazed aluminum tubing. More details are shown on the right. These pages reflect reviewing all the projects to set priorities. X6 was an interesting gyro study where hardware was purchased and led to interesting investigations. It still remains a strong observatory candidate, perhaps adapted to Hubble Space Telescope protocols. I ran some interesting tests with these gyros before abandoning it primarily on this specific hardware. The 8-inch f7 saw first light on September 21st, 1968 and performed well. The These are miscellaneous other studies that were conducted at the time. I also decided to remount my old 8-inch Richardsfield telescope in an integrated fiberglass sphere tube assembly. The cross-section drawing right is a good representation of that design in a 20-inch diameter sphere. Below right was a first look at a 12.5-inch f5 Richardsfield Newtonian, a sizable telescope for its day. Further investigations were explored for a commercial kit. The start of the 12.5-inch. Surprisingly, the size and scale brought a new excitement to the tasks. And right, a design for a workbench to handle the few plaster turning models that would be required for the 12-inch. In a change of pace, these photos represent the preparation for a total solar eclipse tour in Mexico in 1970. My 8-inch RFT was wrapped in foam padding and used as a suitcase to be checked in as baggage, and still usable in the field. I had also set up my smallest telescope for my 16mm Bolex movie camera. The last photos from that eclipse appear on this slide on the left. To the right, a plaster cast is set up to grind it spherical. This is for the 30-inch diameter fiberglass shells. Sand is placed into the large cast and a smaller plug is used to grind them true. There was small damage to the fiberglass shells of the 8-inch RFT after returning from the eclipse. I decided to refurbish those parts as well as make a new basin for it. Lower right are comments related to the large 30-inch sphere shells which are in work. The photo right gives a sense of the mass distribution of this large Spheremount. More details on the basin, the tooling for the large scope, and the adjusted weights and balances of the parts that were actually made. 17 months of build activity passed unrecorded. Catching up on the photos which were taken is a primary mirror bulkhead and the mirror cell, which must be flexed to slip over the mirror and to snap back. Lower right is the fiberglass and plywood ring laminate that will be bonded into the back of the sphere. This slide captures the description of the spider diagonal holder and the photos of the plaster buildup, the epoxy glass skin layup over it to make the holder. It is designed with a spherical backside, so when the holder is tilted and adjusted to align the mirror, the on-axis point on the mirror does not change. This slide records the building of the structural fiberglass parts. First the tooling, and then the parts and their assembly. This cutaway drawing shows the complete assembly of all the parts, as well as the primary mirror cell and carrier that allow transporting the mirror separately and then dropping it into place. Most of the material shown so far can be seen broken down in greater detail in the YouTube series of videos I have already posted. Of novel interest for your information is a free vision finder shown on the 12.5-inch, which has some history or connectivity to my work at General Motors. The end of the bulk of development work fell about with the completion of the 12.5-inch in 1972. Currently, I've been active documenting my past work on YouTube videos. However, I have continued making PowerPoint conceptual designs of advances in the state of the Spheremount art, focused on updates to new multi-mirror and adaptive optic systems, and using a 30-meter telescope as my basis, not to change the TMT, but rather to offer future telescope systems and protocols. While showing my Spheremount at Stellafane, I was very disappointed when I failed to collimate the Cassegrainian prior to nightfall. This slide represents a procedure I developed for laser collimating the primary mirror in daylight that would have solved my problems on that day. This is a summary of the early generation Spheremount prototypes that were built. Payload, as referred to in this table, means the displaced weight of water and, therefore, the total buoyed weight of the telescope. Conceptual design and executive summary was submitted to DARPA, a mass moment-driven Earth telescope. And my background for your information.